6 now. That was easy. Let's do the kinetic theory of gases, which will be kinetic theory, EK, collision frequency, all three of those in one swoop. Okay, I'm going to refer to my lecture notes reader on page, let me find it, 48 and following on the lecture notes. Okay, so, kinetic theory. Just a really brief overview. There's 5 assumptions that you should be aware of. So that's the assumptions on page 48. Gases are tiny, or they take up no volume. They travel in straight lines very rapidly, bouncing around in a random path. They have elastic collisions, there's no attraction, and the kinetic energy is proportional to temperature. This is about 5 assumptions we're making to do the derivation. The derivation basically derives the ideal gas law, and it derives another equation for the kinetic energy. Okay? So in addition to that, there's on the same page 3 mathematical concepts that you should be familiar with. One is, and these were used in the derivation, the kinetic energy is 1/2 mu squared. That's used, we didn't do the whole derivation. Somebody asked about collision frequency. You need to know it's proportional to the velocity, the number of particles divided by the volume. That means, since somebody asked me about this one, the faster the particles go, the more collisions, or the higher the frequency. That's why velocity is in the numerator. The more particles, capital N, the more collisions. So that's why that one's in the numerator. And then the volume's the opposite. The larger the volume, the less collisions, because there's more space. And so that one, that's why that one has to be in the denominator. It's an inverse relationship. This is where collision frequency comes from. You wouldn't have to calculate it. Any question you get on collision frequency would be purely conceptual. Okay, and then we gave you one on capital I, which in this chapter is momentum. It's the mass times velocity. The mass, the harder the hit, the higher the momentum, and the velocity, the faster it's going. Again, the harder the hit, the more momentum. We put these together, especially the bottom two, to start the derivation. We said pressure is proportional to collision frequency times the momentum. And you could put those formulas together, and that's how our derivation started, which we didn't really do the derivation, but that's where it would have started. And if you're curious, it's in the reader. This, a result of doing this, came to the 2 following equations. So as a result, we got to the ideal gas law, and we got to EK squiggly equals 3/2 RT. Okay, so those are 2 things derived. R is experimental, so R came out, R comes from experiment. All right, somebody asked about EK squiggly. The difference between EK squiggly versus EK, both are kinetic energy, but EK without the squiggly is kinetic energy in joule units. EK with the squiggly on top, meaning the one with the equation, is in units of joules per mole. That's the only difference, the units. So with the squiggly, it's joules per mole. Otherwise, there's no conceptual difference. A couple concepts that came out of this. So at the same temperature, say molecules in this room, what do we know about their kinetic energy? They're the same. You have to be more specific. Are they identical, or is the average the same? Average. So the kinetic energies are not identical, but on average they're the same. Okay, so that's an important difference. The other thing we get out of this, the heavier the molecule, the faster or slower it goes. Slower, yeah. So that's another thing, concept came out of this whole set of derivations. Also, the kinetic energy is also equal to 1/2. It's this, but when you change the per mole unit, you have to change the equation a little bit. And the way I wrote it in class is capital M, which is two ways to write the same equation. By the way, this R is what? 206 liters atmospheres per mole Kelvin. And this R, yeah, the other one, 8.3145 joules per mole Kelvin. Okay, besides the ideal gas law, where else would you use this R? The combined gas law drops out though, so you wouldn't need it there. Besides here, where do you use this R? Nowhere else. Besides here, where do you use this R? Everywhere else. Okay? This equation is one of the equations that are not in SI units. In general, every other equation is in SI units. What's another exception where we don't need SI units? This is not SI units right there. What else? Well, what equation? What equation does not need SI units besides that one? Graham's law, that's right. Anything else? Any ratio equation. Graham's law, Boyle's, Charles, Avogadro's, etc., etc. Anything with a ratio or that one doesn't need SI units. Everything else, I recommend SI units. Okay? So it's not one of those ratio equations or this one. I recommend using SI units. It should be easier. All right, also out of this, eventually we got the root mean square velocity. Oh, let me circle the equations you'll most likely use mathematically. Mathematically, you use this one, this one, this one. I tend not to use this one. Why not? It's a little simpler just to use this one because you only need temperature and they calculate the same thing. But sometimes you might use this one. But because I never do, I'll just circle that one for you. Okay? So this is the root mean square velocity. The main thing about this, temperature is Kelvin. R, which R? Left or right? The right, because every other equation uses this one. And molarity? No, don't be crazy. Molar mass in what units? Kilograms, yeah. Okay. And then somebody also asked me about this. So something else that eventually came out of all this is Graham's law, which it says property of, say, gas A over property of gas B equals the inverse of the molar masses. And that's true for several properties. The root mean square velocity, distance, amount, that all works for it. It also sort of works for time also, but time is not inverted. Okay. Time would look like this. It's the only one that doesn't invert the molar masses. Okay? Every equation I've written down so far are all plug and chug. There's the only one that has to get a little more involved is the ideal gas law because that can involve a density or a molar mass. But otherwise, everything else should be just straight up put it in the equation. All right, let's see what we did here. I'm going to say more about this chapter, but are there any questions on kinetic theory while I'm on it? Yeah? You have to know the names of the ratio equations, so that's it from the gas laws, you mean Boyle, Charles, etc. If you know those, that's fine, but I won't quiz you on those. You would have to know things like, I have to think about it. What would you have to know? As far as equation goes. Like the ideal gas law, I guess? Might be nice to know. Dalton? Yeah. I'd have to think about it. But that's a good start. Any other thing else about this stuff? Yes?
Why is it when temperature increases, there's a higher chance of molecules directly shut off?
When temperature decreases, so that's an important concept for the real gases. When temperature decreases, what happens to the molecule's velocity? It has to go down. So that means they're flying past each other slower. So what happens to the attraction? More likely, less likely? More likely. Just because they have more time next to each other. You'll notice if we're talking about ideal gas, we're all relatively at higher temperatures, meaning above 0 usually, or maybe you can drop it down even lower, above -50 Celsius or something for ideal gas. Once the colder you get, the more real it gets. Okay. Last, any questions on this before we move on? Yeah. You mean when you're showing your work? The question is, when you're plugging numbers into a formula, do you need to show units? You don't. I would say generally, the more you show, the safer it is for the TA who's grading it. Generally, yeah. At some point, you probably should show unit work. If you're not showing it in the equation, at least on a separate calculation. Yeah. But I would say in general, showing more is better. It just clarifies if the TA, sometimes the TAs will come across something, they're grading 1 of 500, and it's that one that you're like, not sure if they knew what they were doing. No benefit of the doubt for you. Knock you off. You see what I mean? Okay. Let's do units, since you just asked. You'll see there's pretty much a unit question on every one. First, a little summary. You need to know what all these stand for. So somehow get it in your brain, because I'm not going to tell you. Okay, then I would do something like, say, wait, I have to think about this. Let me find a good, ugly equation, or something that would be scary looking. You know? We'll do a little example.
Oh, no.
Yes. Oh, I like this one. Okay, so simplify. Awesome. There's a couple ways you could actually do this, a faster way and a slower way. I'll just do it the slower way, assuming you don't see the pattern. There is a certain pattern right now, but assuming you don't see that, let's do this the slow way. All right, let's write it out. Joule squared, second squared, kilogram, meter squared. Let's write out the joules, is usually where I start. Newton meter squared, so they're both squared. Still have the second squared there. Kilograms, meters squared. So notice the meters drop out. I'll do that in a different color. Okay. Now let's substitute in for the newtons. The newtons are kilogram meter per second squared, but that's squared. So that's squared, and the fourth. There's the newton squared. I've still got the second squared and the kilograms. All right, let's simplify a little bit. Kilograms gone. 1 of the kilograms are gone. 2 of the seconds are gone. Let's see what I got. This is a kilogram meter squared second squared. Now I'm trying to figure out what this is. It doesn't look like a Pascal. It kind of looks like a Newton a little bit if I write it like this. Right? You see how it looks like a Newton? So I'd say, oh, that looks like a Newton meter, which is a joule. Oh, this mess was a joule. Okay? Which, if you recognize this is kilogram meter squared second squared, that's a joule actually. So you can just drop it out if you did the easy way. All right, so if you have any fear of forgetting this, the first thing I would do on the exam is write this on the back page. Like, it just take you 10 seconds. And then you don't have to worry about remembering it. All right, next. Dalton over water. Dalton over water. are relatively easy questions. You just have to run through one or two. They will get harder or easier. We can just kind of word them slightly differently. So let me go to the page it's on. It's on page 58 of the reader, page 58. Did you mostly hear me? Most part? Okay. So, first of all, the setup. There's a reaction that happens in a container that has a little hole with a tube. The tube goes into another container with water. In the water is an upside down marked cylinder, basically. And then this tube bubbles in here. Initially, the beaker is full of water and the whole cylinder is filled with water. As the reaction gives off a gas, so this is for gas-forming reactions, the water level starts to go down. Because it was at the top, it starts to go down. So the water's all here. Okay? So that's all filled with water. In here, now because that's gas, that has a pressure. We call that P total. That's due to what two things? Yeah. The pressure of the gas from the reaction, so the gas that's coming off the reaction, whatever that is, plus the pressure of the water, because the water is going to have a vapor pressure, and it will contribute to the gas pressure. Okay, now let's talk about where all these come from. Where would I find that dumb thing? If I'm not asked to calculate it. It could be given, and what might it be called? The barometric or atmospheric pressure. Barometric or atmospheric pressure. That means the pressure you read off a barometer. Okay? Like the pressure you're experiencing now from the atmosphere. That pressure. Okay, where the heck do I find that? Table. Let's say it's an exam. I have my exam reader here. If you didn't look at page 4 and 5, you should have, because that's where all the exam givens are. And it's a table that looks like this. So basically, all you need is the temperature. If you have the temperature, say it's 50, that vapor pressure, that's the partial pressure of water. Okay, so that's the partial pressure of water right there. So you just use that number, plug it in, oops, whoa, right here. Okay, so that table's in the back. I have occasionally, just for fun, said, oh, we're at a temperature of 50, there's a certain and it's water, there's a certain volume, there's a certain blah, 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 garbage, garbage, garbage. What's the vapor pressure of water? And I just want you to write that number down. Okay? So if I'm talking about water and I give you a temperature right there. Okay. Cool. Okay, there's one more equation that is almost always used here, and it's the ideal gas law, where this is the moles of the gas there, and this is the pressure of the gas. So you need to notice that these two are the same variables. That P gas connects both equations. The P gas connects both equations. So now it just depends what we ask for. We could ask for P total, in which case you have to know all of this stuff. You have to know this, this, and this. Okay? Find P gas, you put it in here, you add it up. We could ask for the moles of the gas, in which case you know this stuff. You find P gas and you use the molar. It depends what you're asked for. So I would write down these two equations, and then I would kind of circle the one you're asked for, and realize that you better be able to get everything else either from the question or the table on the back of the exam. That's it. So now it's plug and chug for two equations, but you never know what we'll ask for. Now there was one, I think, on a homework where we didn't give you the moles of the gas, but we gave you the reaction, and you could use stoichiometry to find the moles of the gas. Okay? So that's an option too, it's a little twist. So the moles of the gas, is the only one that we can kind of twist it up on you, and you get that from stoichiometry. We'd have to give you the reaction and say the mass of another compound in the reaction. So you can use stoichiometry to get to this. Okay. So that's the basics. Later, if somebody has a question, we can work through it.